And welcome, folks. This is Mr. Callen coming for today's math lesson for Wednesday, May 6th. Google Classroom might look a little similar to mine. Read the overview. I'll go through that in a second. Optional Khan Academy article if you learn better or faster or more efficiently that way. Also new for today, optional and experimental live teaching session, math lab classes 2 to 2:30 on Wednesday, May 6th. Use the code Callen1234. Math 8 classes, hours 5 and 7, you can use the code Callen57, and that's from 2:30 to 3. Got a video that you're watching right now. Complete the assignment and then some exit problems. You might realize what's coming. I want to talk about the live teaching session I'm going to try. Your screen might look a little different than mine. Instead of join or start meeting, it might say enter code or whatnot. And again, the code for the math lab classes will be Callen1234, and that'll be between 2 to 2:30. Code for math 8 classes Callen57, Callen57 for hours 5-7. That'll be 2:30 to 3. The exit problems, you might already realize what's coming after you enter the usual name, date, and period. How are all these problems on the homework similar? How are they all different? And then write yourself a step-by-step series of instructions for how to describe and describing how to convert a repeating decimal into its equivalent fraction in simplest form. I want to talk to you a little about where we've been before where we are going. Perhaps you remember from 7th grade, even 6th grade, how to turn terminating decimals into fractions or mixed numbers. From there, we're going to go to the 8th grade of how to turn repeating decimals into fractions or mixed numbers. So walk down memory lane. How do you turn a terminating decimal into a fraction? Well, remember we have place values. For instance, 4 is in the tens place, and naturally below that, 3 is also in the tens place. Of course, if you have more digits, you have more place values. So 35 would be hundreds. Again, 1 is in the tens place, 17 hundredths, or 175 thousandths. So we can pretty quickly rewrite terminating decimals into its equivalent fraction or mixed number. For instance, 4 tenths, we can just write 4 tenths. Yes, that will reduce. In fact, it's a better answer, although they are the same amount. Anytime something's even, you can reduce by 2. 35 hundredths, we can rewrite as 35 over 100. And yes, because those both end in a 5 or a 0, we could reduce that to 7/20ths. Again, same amount, but 7/20ths, better way to write it. 2 over 5, better way to write it. Then, of course, we have 2 whole pizzas, and then we have a small portion of a pizza. That would be 2 wholes and 175 thousandths. You could reduce by 5 and 5 again, or you could reduce by 25, still having 2 wholes, but now we have 2 wholes and 7/40ths. So that's just a little walk down memory lane. The problem is, what happens if those decimals do not stop? For instance, instead of it just saying 4 over 10, what if that 4 is repeating? We cannot just write 4 tenths, nor can we write 44 hundredths, nor can we write 444 thousandths. Every time we continue to have parts and little tinier parts. So there has to be some other way to turn 0.4 repeated into a fraction. To do so, we're going to actually need to use a little bit of our knowledge on equations. Now you see my drawing and you see how I write it with numbers and symbols. A single n here is equal to 0.444 repeated, okay? Remember that all equations must remain balanced. Therefore, if I add another n on the left side, I must keep it fair and balanced so as not to make a crazy imbalanced equation. So we can say that 2 sets of n, or 2 n's, is equal to 2 sets of 0.4 repeateds. I guess you could call that 0.888, so on, so on, so on. Likewise, we could say that 3 n's are equivalent to 3 sets of 0.4 repeated, keeping it fair and balanced. Or 4 n's are equal to 4 sets of 0.4 repeated. Or 5 n's are equal to 5 sets of 0.4 repeated, and so on and so on. At this point, you can say it, as long as we are equivalent to both sides, we can keep going on for a long time. Even up to and including 10 n's are equal to 10 sets of 0.4 repeated. Now, I'm going to go ahead and rewrite 10 n's as simply 10n. But the question remains, how can you simplify 10 of a number that goes on forever? Now, 0.4 repeated plus 0.4 repeated, yeah, sure, that could make 0.8 repeated. You can kind of picture 4 and 4 and 4 and 4 and 4 and 4 makes all those 8s. But what happens when you add more 4s? And there are more place values and more carrying and more regrouping to add. So I'm going to pause for a second, and I'm going to talk about multiplying something times 10. What can happen to the place value? So let's go ahead and look at this multiplying times 10 and see if we can see a pattern. Now we start off with the basics. You know that 4 times 10 naturally would make 40. 44 times 10 would make 440. 44,000 times 10 would make 444,000. Now think about what we were just talking about with scientific notation. The idea that multiplying by tens or powers of tens doesn't just add zeros, but adds place values, if you will. So if we multiply 4 times 10, that will move the place value 1 time to make 40. Likewise, 44 times 10 moves the place value once. 10 44s would be 440. Then multiply 44,000 times 10, and so on. So really, to multiply by tens, it's not just zeros. It's really about place values. So let's continue that pattern. If we multiply 44 times 10, if we multiply 4 and 4/10 times 10, that would naturally make 44. If we multiply 0 and 4/10 times 10, that would make 4 wholes. I suppose you could write the 0 if you absolutely want to. If we multiply 44 hundredths or 44 pennies times 10, we would have $4.40. What about if you multiplied 444 thousandths times 10? Well, follow that pattern. It changes the place value, and we get 4 and 44 hundredths. What if we multiply a decimal that goes on forever times 10? Well, again, it's simply going to change the place value so that we would now have 4 wholes, but we would still have all those 4s left over after it. In other words, 0.4 repeated multiplied by 10 will change the place value so that we have 4 wholes and still have all those parts to infinity. And so we'll remember, anytime we multiply by a power of 10, it moves the place value. Because there's only one 0 here, 10 to the first power, 0.4 repeated multiplied by a power of 10, multiplied by 10 to the first power, will be 4.444444 repeated and so on. So we have taken our equation 1n, or a single n, and I can rewrite that very lightly as a single n is equal to 0.4 repeated. And as long as we're fair to both sides, 10 of those would be 10 n's. And 10 sets of 0.4 repeated would be 4 wholes, 0.4 repeated still. Now here's the idea. I would like to simplify this equation by taking away 1n from 10n. Now remember, if I do anything to one side of an equation, then I better be fair and do it to the other side. Showing it pictorially, I can simply cross off one of those n's. Okay, 10n minus 1n is 9n's. On the other hand, what happens when I take away a single one of those? A little more complicated, but think about this by looking at the equation on the right. If I have 4 dimes and I take away 4 dimes, what do I got left? No dimes. If I had 4 pennies and I take away 4 pennies, no pennies, no hundreds left. What if I take away 4 thousandths from thousands, or 4 10,000ths from 4 10,000ths? And so on forever. All of a sudden, what is left over is 4 wholes, take away 0 wholes, and we don't have any of those decimals that go on forever and ever. We simply have 4 wholes. Now this sets us up quite nicely to finish this. I want us to pause for a second and think about, what did we really want to know? Well, like most equations, I want to know what a single n is, not what 9 n's are. So how do we figure that out? Well, we're simply going to take 9 n's and split it up into 9 parts. As long as we're fair to the other side, take those 4 wholes and split it up into 9 parts. Now what this leaves us with is a single n is equal to 4 split up into ninths. Whoa, wait a second. Let's just pause and review what we talked about here. We said at the very beginning of this expression, these equations, that a single n was the same as 0.4 repeated. But now what we also know is that a single n is equal to 4 ninths. So what you can imagine is by taking away the middle part, if a equals b equals c, if 0.4 repeated is equal to 1n and 1n is equal to 4 ninths, that logically says that 0.4 repeated is the same as 4 ninths. We just took a repeating decimal and changed it into its equivalent fraction. Beautiful. Now, I just wanted to show you this visually, why we would multiply by a power of 10, why we would take, instead of just a single n, 10 n's, why we would take, instead of just 0.4 repeated, 10 of those, which ended up being 4.4 repeated. And then we used our equation skills to solve for what that 1n is. Let's go ahead on to our homework assignment and see if we can continue on changing other repeating decimals into their equivalent fraction. So I'm going to try to remember to put some answers in, and it looks like a lot of these did not copy well. I apologize for that. I don't know what's going on with the computer. So if yours also looks kind of weird, that 0.8 with the repeated bar, you might just want to extend that repeated bar over there just to help you out. So let me, like normal, go through a few odd problems. Feel free to fast forward, skip some parts, rewind, pause for a second after a problem, do your homework, do whatever is comfortable for you. We are asked here to convert the decimals with one repeating digit into equivalent fractions. Oh, don't forget simplest form. If you can simplify, always try to do it. Number one, we're going to let n, and really you could use any variable you want, equal to 0.8 repeating. I'm going to draw a few eighths here just to help me out. Now, as we said before, we want to set up a new equation where we're going to multiply by some power of 10. So if I multiply 1n times 10, picture the old problem, rewind if you want to go back to that and see it, that would make 10 n's. If, however, I multiply 0.8 repeated times 10, that changes the place value so that we now have 8 wholes, and we still have all these 8s afterwards, so on and so on and so on. So now we have two equivalent equations, and if we subtract those, as long as we're fair to both sides, we will yet again have an equation that makes a true statement. Now on the left, if you have 10 n's and you take away 1 n, that leaves you with 9 n's. On the right, you have 8 wholes, take away 0 wholes, and meanwhile you have 8 minus 8, and 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 bye-bye, sayonara, arrivederci, adios to all those place values. All those portions are gone. Now this is great, but I don't want to know what 9 n's are equal. I would like to know what a single n is equal to. So in order to do that, let's split it up into 9 parts as long as we are fair to both sides. Now in this case, 9 n's split into 9 parts is a single n. Good, that's what we want. And if we have 8 wholes split into 9 parts, aha! So where 0.8 repeated, we can rewrite as a fraction in simplest form. 8 and 9 do not reduce, and we are finished with number 1. 0.8 repeated is the same as 8 ninths. Let's go on to number 3 right below it. Sorry about that formatting, where we set a single n is equal to 0.5 repeated, and I'm going to give myself a few 5s just so I can picture it out. Now, what were to happen if we would take 10 of those? Well, 10 times n would be 10 n's, and as long as I'm fair to the other side, take 10 of 0.5 repeateds, that's going to change our place value so that we now have 5 wholes, and we still have all those 5 portions, parts, pieces to infinity. Now what we have are two equivalent equations. If we subtract both, as long as we are fair to both sides, again, it will make an equivalent equation. On the left side, 10 n's minus 1 n, 9 n's. And on the right side, all the parts, 5 minus 5, 5 minus 5, 5 minus 5 to infinity, get canceled out. But we do have 5 subtracting 0, which is 5 wholes. Our goal is to find what n equals, not what 9 n's are equal to. So let's go ahead and divide both sides into 9 parts. That will leave us with a single n, which is exactly what we wanted on the left side. And 5 split up into ninths is 5 ninths. That tells us that while n is equal to 0.5 repeated, it's also equivalent to 5 over 9. If you wish, pause right now, go to the even problems. Otherwise, let's keep on going to some odd problems on the back side. Off to number 5, where we have 0.16. Now let's take a look here. If we multiply both sides by 10, 10 times n is 10 n's. And if I multiply this repeating decimal by 10, it moves the place value one time to make one whole, 0.616161, and so on. Now, some of you might be looking at this funny, and rightfully so take a look at what happens. It appears at the beginning we're in good shape. 10 n's minus 1 n is 9 n's, but now we have something kind of weird. See, 1 whole minus 0 wholes, okay, 6 minus 1 is 5, and 1 take away 6, wait, we can't even do that. Wait a second. Those place values will not, in fact, cancel out. So that didn't reach our original goal of getting rid of all the parts. We will still have some crazy, ugly fraction. Multiplying by 10 did not work. So I wonder if multiplying by 10 or 10 to the first did not work. What about multiplying by another place value? What about 10 to the second or 100 of them? So if I multiply and imagine that picture on the scale, instead of 10 n's, we would have 100 n's on the left side. On the right side, we're now multiplying by 10 to the second power, which again will move the place value, but instead of once, it moves twice. Think about what this will look like. We now have 16 wholes, 0.16, 16, 16, and so on. Now imagine what's going to happen when we subtract. We know with equations, as long as we're fair to both sides, we will still keep a fair, balanced equation. Interestingly, on the left side, we're now subtracting 1 n from 100 n's. That makes 99 n's. Now let's take a look at the right side here, where now we have 16 wholes minus 0 wholes would give us 16. And what happens to the right? 1 minus 1 is 0, and they cancel. 6 minus 6 is 0, and they cancel. 1 minus 1 and 6 minus 6. And now we've reached that goal. No more parts, pieces, or portions because the place values lined up again. So that's going to be an important difference from the front page to the second. Remember, as we go through in the exit problems, how are the problems similar? How are they different? And then write yourself a step-by-step series of instructions. All right, remember, goal, n equals. But right now we have 99 n's equals. Well, let's just split that into 99 parts, as long as we are fair to both sides. 99 n's split into 99 parts gives us 1 n, and you guys don't have to write that one, you know that. Meanwhile, we now have 16 split into 99ths, and bam, therein lies our answer. We have now realized that 0.16 repeated is the same as saying 16, not hundredths, but 99ths. Learned a little valuable lesson. If you wish, let's go on to number 7 and kind of use the same strategy. In this case, we have 0.32, and both the 3 and the 2 are repeated. Now, I wonder what would happen if we would multiply by 10 again. If we were to multiply the left side by 10, 10 sets of n is 10 n's. And if we multiply the right side by 10, moving it 10 to the first, one place value, we'd get 3 wholes, 0.2323, so on. But once again, we will see that the place values will not cancel. In other words, we would still have a repeating decimal going on and on forever, and that is not what we want. So multiplying by 10, or 10 to the first power, won't do the trick. So let's do something different. Like the problem above, instead of 10 to the first, let's multiply by 10 to the second. In this case, 100 sets of n is 100 n's. And multiplying 0.32 repeated by 10 to the second power moves the place value 2 times, leaving us with 32 holes, 0.32323232. So let's ask ourselves, did that do the trick? Are we getting what we want to get? 100 ends, take away 1 n is 99 ends. 32 take away 0 is 32. Meanwhile, 3 take away 3 is 0, and 2 take away 2 is 0. And yes, in fact, going on forever, we have all those parts, pieces, or portions canceling out and none left over. Let's go ahead and take 99 ends and split it into 99 parts, as long as we're fair, and split 32 ends into 99 parts, leaving us with a single n is equal to 32/99. Does that reduce? I don't believe so. We already are in simplest form. And so we have now arrived at another answer that 0.32 repeated is the same as saying not 32 over 100, but 32 over 99. So at this point, folks, I might do a couple extra problems, but if you wish, why don't you go ahead and start the homework? Again, if your homework does not look right, I apologize for that. Something's going on with the formatting, so simply take your pen and extend the lines, the repeating bars, that includes the front page as well, to 0.6 repeated, 0.2 repeated. I'm going to continue on with some more odd problems. If you wish, follow along. As I go through these problems, you might recognize these questions. Is number 9 more like numbers 1 and 3 on the front side, or more like numbers 5 and 7 on the back? Well, there apparently is one repeating digit. So I believe if we simply multiply both sides by 10 to the first power, it should do the trick. Therefore, 10 times n is 10 n's. 10 times 0.1 repeated is 1 whole, 0.111 repeated. And it does appear that our place values will line up. So let's go ahead and take these equations and simplify them by subtracting each fairly. 10n minus 1n is 9n's. 1 minus 0 is 1. 1 minus 1, however, is 0, and all those place values will cancel out. Goal being to find out what n is. Let's take 9n's and split it into 9 parts. Let's be fair to the other side. And in this case, that tells us that a single n is equal to 1/9. And so 0.1 repeated is the same as saying not 1 over 10, but 1 over 9. On to number 12, where we will have 0.12 repeated, so 0.1212 and so on. Now I ask myself, is it more like the front side, or is it more like the back side? And I see 2 repeating digits here, so I'm going to multiply by 10 to the second, or 100. Now 100 sets of n is 100 n's. Meanwhile, what happens if we multiply 0.12 repeated by 100? It's going to move the place value twice, leaving us with 12 holes, 0.121212, going on and on forever and ever. As I examine the place values, it sure looks like the 1 and 2's will line up and cancel out. So let's go ahead and subtract both equations. 100n minus 1n is 99n's. 12 minus 0 is 12. 1 minus 1 is 0. 2 minus 2 is 0, and so on. We have successfully gotten rid of the parts. Let's go ahead and split 99 parts into 99 and split 12 into 99. That will tell us that a single n, but by now you realize that you do not have to write the 1. A single n is equal to 12 over 99. Hey, finally we get one that will reduce. Both 12 and 99 are divisible by 3, and so we get 4 over 33. Now, don't get me wrong. If I write 0.12 repeated is the same as 12/99, technically that is correct. If I write it's the same as 4/33, again, same amount of pizza, just a different way of writing or representing it. Quite frankly, I think 4 over 33 is the best answer. You might lose a half a point if you do not reduce on the quiz coming up. Now, I left some challenge problems for you at the bottom. 4.63 might look a little different. Along with this, number 2 is supposed to be 0.08, and only the 8 is repeated, not the 0. So something different to think about for those of you looking for the challenge. So please continue on with this assignment for numbers 2, 4, 6, 8, 10, 12. I might go back and put in a few answers there so you can kind of check yourselves But still, show the work because I'll be checking the work. That's what will be graded. A reminder that when you're finished, go back and complete those exit problems, especially focus on how are all the problems similar, how are all the problems just a little different, and then writing yourself a step-by-step series of instructions for how to convert any repeating decimal into its equivalent fraction in simplest form. And lastly, I will remind you, if you're interested in the live action with Mr. Callan coming at you, to go ahead, check out during 2 to 2:30. Callan1234 is the code on Google Meet. 2:30 to 3 for my other classes, hours 5 and 7. You're going to write Callan57 is the code. Looking forward to seeing some of you guys then. Take care, guys, and let's grow.